welcome back to this session, and we now have a slightly different way of projecting things. So, we are hoping that this will be better than what we did last time. Question?
In specific how y are taking positive sign for the tensile force towards the outward direction, why can't we take the negative sign for this condition? Angle of contact. So questions পড়ে নিয়ে নেবেন।
আচ্ছা, তো ডিফারেন্সটা কি হলো উপর থেকে নিচ্ছে কি? So, what we have seen is that the pressure field can be written as minus rho g dot r plus a constant. So, this holds under two conditions. One is fluid at rest, the other is rho equal to constant. Now, let us take a case where you have say water in a tank. So, let us say this is the water, and above you have air. So, I can call this say fluid 1 and I can call this fluid 2. So, in this fluid we can say that P is minus rho 1 g dot r plus some constant, where rho 1 is the density of water. Rho 1 is equal to rho water, which you can say is say roughly 1000 kg per meter cube. Now, density of air of course, will depend on temperature and pressure, but under many circumstances it can be treated roughly as constant. So, if I say that here rho 2 is approximately constant. So, this will be true if the variation of density and pressure between certain points in this region is small. Then you are going to have P is equal to minus rho 2 g dot r plus another constant. Okay. Now, rho 2 here can be taken to be what we are calling the constant density of air at this temperature and pressure. So, that may be of the order of 1 kg per meter cube, or maybe at STP 1.2, 1.29, whatever it is. So, you see that when you have two fluids, in this case water and air, the ratio of the densities is of the order of 1000. Okay. So, under those conditions, the change of pressure with height in the air can be neglected, and you can say that here P is approximately say a constant, which is your atmospheric pressure. We cannot say the same here in water, because if you take any 2 points in water with a, if this is the direction of gravity, if these 2 points are distance h apart, the difference of the pressures between these 2 points will be rho 1 g h, as you can see from here. So, that cannot be neglected. So, I will draw the figure again. Now, let us choose a coordinate system where say z is upwards and this could be your x, this is the origin, and this is the level of water. This height, let us say, is capital H. So, if I say that in the air above the pressure is a constant, which is your atmospheric pressure, then you have a boundary condition that at z equal to H, P is P atmosphere. So, this base of this tank is described by z equal to 0, and this free surface, which is the interface between water and air, is z equal to H. So, if you neglect surface tension effects, then the pressure at a point below the interface and the pressure at a point just above the interface, they will be the same and equal to the atmospheric pressure. So, this is the boundary condition which you can use. Now, with this coordinate system, the z axis is vertically and pointing upwards and g is downward. So, we have seen that P is minus rho g z plus C. This is a P at any z. Now, if I evaluate it at P of, so this is P of z. If you look at P of H, that is minus rho g H plus C, that will be P atmosphere. This gives you C equal to P atmosphere plus rho g into capital H. So, if you substitute this into this expression, you are going to get P of z is equal to P atmosphere plus rho g into H minus z. আমার ফোন তার জন্য ফোন লাগাচ্ছে। আচ্ছা সাইলেন্টলি আছে। আচ্ছা now consider a point P over here. So, this distance then according to our coordinate system is z, the height of the point P above the base of the tank. So, what you have over H minus z then is this height, we can call it small h, because this total height is h and this is z. So, h minus z is small h, which is the depth of this point P below the free surface. So, we can say that it is P atmosphere plus rho g into H. Now, this rho of course is the rho of the water. So, you see that the pressure increases with depth as you go downwards, and it is a linear increase. Now, we can look at forces on submerged bodies. So, once again let us start with that simple example where you have water in a tank. Now, suppose you have a solid plate which is in the water. So, you have air above and you have water. And we are interested, let us say, in the force exerted by the two fluids on the top surface of this plate. So, let us draw a free body diagram of the plate. Now, you see that if I consider 2 points on the top surface of the plate, say this one and this one, they are the same height below the free surface. So, the pressure is going to be the same. So, you have a distributed load which you can show by means of these arrows, and this magnitude in Newton per meter square is the pressure at this height, which is P atmosphere plus rho of the water into G into H, where H is this constant depth. So, this is a constant. So, if you want the force, if I say this is a Z, if you want F Z, we know that it is going to be downwards, because it is a fluid cannot exert a tensile force, it is going to exert only a compressive force. So, the force on the top surface is going to be downwards, and if you look at the force exerted by the fluid on the bottom surface, that is going to be upwards. So, this is going to be now negative into simply this P into the area of the plate. So, this was simple because the pressure was not varying from here to here across in the horizontal direction. Now, let us consider the same example and a plate which is vertical. So, this is a solid plate, and let us say we are now interested in the force exerted on the left surface here. So, I will draw here a free body diagram of this solid. Now, you see that as you move along this surface, the depth of these points below the free surface is increasing. So, the pressure is not a constant. So, if you show this loading, you have a linear increase in the pressure. Now, if you want the net force on the top surface, you have to integrate. It is not simply the pressure into the area, because we do not know which pressure to take. So, if I take a small area element here, if you call it dA, an infinitesimal area element, then on this area element, if you look at, say, now if I call this x, we are now interested in the force in the x direction. So, if you look at dFx, it is going to be the pressure at that point into dA, and this pressure is now varying with the vertical height. So, if you want the net force on this surface, it is going to be integral of dFx, which is integral of P into dA. So, you see the utility of finding the pressure distribution. It can be used to find what is the force exerted by the fluids on submerged solids. Now, we had looked at a case where the two simple cases where you had plane surfaces, one was horizontal, one was vertical. You can now have a case where it is inclined, but still a straight surface. Now, if I want the force, so this is the water again, and this is air. If I take a area element here, the force exerted by water will be normal to this. So, it is going to be perpendicular and it is a compressive force. So, we know the direction. Now, if I take another area element here, the force is in the same direction. Similarly, you take any area element, the direction of the force is the same, but the dF is going to be different, and you can get it by integration. So, we are going to derive expressions for the net force on such a surface, and if I say this angle is theta, the first case which we looked at, okay. The first case corresponds to theta equal to 0 and the second case corresponds to theta equal to 90. Now, we can also look at curved surfaces. So, let us say you have a solid surface which is now curved. Now, if I take a area element here, the force due to the pressure is going to be in the direction normal to this. Now, if I take another area element, its orientation has changed. The force is going to be again normal to this. I can see that this direction of this force and this force, elemental forces, they are going to be different. So, when you want to find the force on a curved surface, you have to account for both the change in the magnitude of the force as well as the direction. So, first we will find forces or force on plane submerged surfaces. And we will consider the general case. So, suppose I say this is the water level or could be any liquid, above we have air. So, we know that here the pressure is atmospheric pressure. So, let us take the simple example where the fluid is water, a liquid with constant density, and you have a surface, plane surface of arbitrary cross section which is inclined. So, this is the direction of gravity, the vertical direction. So, if I extend this line, let us say this angle is theta. Now, if I draw the other view here, it could be a lamina of arbitrary shape. Now, what we will do is we will put a coordinate system with the origin at the centroid of this surface. So, let us say the centroid is here. So, we will take its projection on this face is surface is here. We will take a coordinate system where now z is not vertical, but perpendicular to this surface. So, this is my z and this is y, let us say. So, the top surface of this submerged solid is described by z equal to 0, the equation of this. Now, on this view, if I show the y axis, it is this way. So, the y axis is this inclined line which goes and meets the free surface here, and this angle is theta, and we will say this is x. Now, let us say we want the net force on the top surface. So, we will take a area element here which is say dA, and we know the pressure here is P. So, if you look at dF, the force exerted by the water on this small area element, we know the magnitude is P into dA. The pressure is the intensity of the force. So, this is in Newton per meter squared, and this is meter square. So, this gives you Newton. Now, if you look at the vector force, then you have to say what is the direction. Now, we know that the direction is normal to this. So, it is in the k direction, but we have to put a minus sign because it is a compressive force and it is in the minus z direction. Now, I can take any area element, the direction always remains k minus k. So, if I want the net resultant force vector, this is integral of this df, which is minus integral of p dA. Now, I can take the k out of the integral because it is a constant. So, I can say that f is say f r minus f r into k, where f r is the magnitude of the resultant force. So, this f r then is integral of p dA. Okay. So, later on we will look at forces on curved surfaces, there we have to account for the change in the direction. Now, you will see the utility of the vector notation. We can get a compact expression for this f r. So, we will write p as minus rho g, sorry, not minus, plus rho g dot r plus c. So, if I expand this, this is rho into g x x plus g y y plus g z z plus c. Now, I will draw the coordinate system again. This was the plate, the top surface of the plate, and this was z and this was y, and this is the vertical direction. So, my g is in this direction, this is the gravity vector. Now, if I look at the components of this gravity vector, I can draw this vector triangle here. So, this is the y z component and this is the y component. So, this vector I can write as sum of this vector plus this vector. So, you can see that now this angle we had said was theta. So, this angle is theta. If I draw it here, this angle is theta. So, therefore, this angle is 90 minus theta and this angle is theta. So, this the angle is theta. So, we have this gravity vector, and if I look at its y components and z components, this is theta, this is the z component and this is the y component of the vector. So, you can see that the magnitude here is g. So, g z will be this magnitude, which is g cos theta. Now, what is the sign? See, this vector equal to this vector plus this vector. So, this is pointing downward. So, it is minus, and g y magnitude is the length of this vector. So, this is g. So, this is going to be g sin theta, and again it is pointing this way. So, it is minus g sin theta, and g x is 0 because the x axis is horizontal. So, if I go back over here, this g x is 0. So, you have to deal only with g y and g z. Now, what we want is the pressure on the surface. So, this is the top surface of the plate. P s is P of x y 0 z equal to 0, because the top surface is described by z equal to 0. So, that is going to be then rho g y y plus rho g z z plus c, and now here I have to put z equal to 0. So, that is simply minus rho g sin theta into y. So, y represents inclined distance along this inclined line, and the sin theta is coming because the pressure does not vary linearly with this y, but with the vertical distance, and therefore, that angle is coming in. So, we want f r, which I am going to write as integral of P s dA, where s is P s is the pressure on the surface. So, this is integral of minus rho g sin theta y plus c dA. So, this I can write as minus rho g sin theta into integral of y dA plus c into a. This sin theta being a constant and rho g being constant, I can pull it out of this integral. Now, if you look at the y coordinate of the centroid, that is defined as 1 upon the area of the plate integral of y dA. So, using this I can express integral of y dA as y c, which is the y coordinate of the centroid, into the area. So, we have now f r equal to minus rho g sin theta into y c into a plus c into. Now, if I factor out the area, you are going to have minus rho g sin theta y c plus this constant. Now, this quantity here you will recognize as the pressure at the centroid, because the pressure itself was simply minus rho g y plus c. So, we have a simple expression for the resultant force, which is the area pressure at the centroid times the area. So, here we have not evaluated what is the value of c. You can if you want, but it was not required for finding this expression. So, if you want to find the resultant force, all you have to do is find the centroid of the area and find what is the pressure at that centroid area. And this also you can write this way as P atmosphere plus rho g, rho of the water into g into the height of the centroid below the free surface. Now, we want to find what is called the center of pressure. we will abbreviate it as C dot P. So, this is the point of application of the resultant force. Point of application of the resultant force. By this we mean that if you have a concentrated load which we call Fr, if it acts at the center of pressure at a point which we are calling center of pressure, the moment due to that resultant force will be equal to the moment of the distributed force. So, if I say that the position vector of the center of pressure is RCP, which we can write as XCP I plus YCP j plus ZCP k, where XCP, YCP and ZCP are the x, y, z components of this position vector. Now, according to our coordinate system, the surface is z equal to 0. So, we had a coordinate z normal to this inclined surface. Okay. And if I draw the other view, I am taking an arbitrary shape. This could be a rectangle, triangle, circle, whatever it is, and we had a coordinate system. Of course, this is not to scale, where this is the centroid. Now, center of pressure may be somewhere which is not the centroid. So, this is x and this is y, and this y is parallel to the inclined surface. This is y. Okay. So, we want the point on this surface, which is shown in this view by this arbitrary shape, such that suppose the center of pressure is somewhere here, then if the resultant force acts at that point, a concentrated load, the moment will be equal to the moment of the distributed force. So, this point, suppose I say is Cp, is somewhere here. Okay. Its view on this projection is here. So, you know that ZCP is 0. So, you want to find XCP and YCP. Now, the moment of this RCP cross the resultant force, this is the moment of the resultant force. So, we want to find RCP such that this is equal to integral of R cross df. So, what we mean is that if I take a small area element here dA, the force on this is dF. This dF force which is acting in this direction has a moment which is R cross dF, and then if you integrate it over the entire surface, you get the net force. So, this is the equation defining this RCP, okay. The point of application of the position vector of the point of application of the resultant force. Now, for this case, we know the direction of Fr and we also know the direction of dF. So, dF vector is dF magnitude into minus k, because it is a compressive force. Similarly, we know that Fr is also the magnitude Fr, this is a vector, into minus k. So, using this, now we let us find the cross products and find expressions for XCP and YCP. Now, if you look at RCP cross F, we can write it as this determinant, where in the first row you write A I J K. Then in the second row we will write the components of the first vector here RCP, and the last third row we will write the components of F. So, now RCP has component XCP, YCP, and the ZCP is 0. Similarly, if you look at FR, it does not have a X component, it is this is FR. So, this is minus T minus FR. The reason being RCP is XCP I plus YCP j plus 0 k. So, this XCP, YCP and 0 we are writing in the second row, and the FR is 0 I plus 0 j minus FR into k. This FR is the scalar which is the magnitude. So, we have minus FR. Now, if I expand this determinant, you see that the k component is 0 and you have only an I and a j component. So, if I look at the thing, we have minus YCP into FR I, and if you look at the j component, you are going to have this subdeterminant with a minus sign. So, you are going to have XCP into FR into j. Now, if you look at R cross df, you are going to have a similar expression. So, we will write I j k in the first row. Now, in the second row we will write the coordinates of the position vector of a point on the surface. Now, for the point on the surface, again x is 0 and this is sorry, z is 0 and you have x and y. So, this R is a position vector of a point on the surface which has z equal to 0, and this is going to be 0 0 and minus df. Okay. The reason being R is x I plus y j plus 0 k. আবার কন্টিনিউ করতে হবে না,
লেখা গেছে অনেক্স করি।
আচ্ছা এটা কন্টিনিউ করতে পারবো না
এখন কন্টিনিউ করতে হলে আপনার রিফ্রেশ করে মানে করতে হবে।
আচ্ছা
নেক্সট পেজ আমি কি নেক্সট পেজ কোড পেজ
আবার
নতুন পেজে লিখ।
আচ্ছা Okay, sorry for the interruption. So, let us start again. We have RCP report আবার করে দেব নাকি,
যেখান থেকে সেটা
কাট হয়ে গেছিল না। RCP cross FR is equal to this determinant I j k. Then the second row we will give the we will write the components of the first vector RCP, which is XCP YCP is 0 and this is 0 0 minus FR. The reason being RCP is XCP I plus YCP j plus 0 k. So, in the second row here we have written XCP YCP 0, the three components of the position vector R. This is x component, this is a y component, this is a z component. Similarly, we know that FR vector is 0 I plus 0 j minus FR k. So, in the third row we write the components of this vector FR. So, it is 0 0 minus FR. So, this turns out to be minus YCP FR I. So, this gives a moment about the x axis and you have XCP FR into j, and there is no k component. Now, this will be equal to integral of r cross d f, where r is a position vector of a point on the solid surface, the upper surface of that plane. So, this again is given by I j k. Now, to write the second row, we write r as x I plus y j plus 0 k, and d f again as 0 I plus 0 j minus d f k. So, if you have a cross b, then in the second row you write the components of a, and the third row you write the components of b. So, here this first vector here is r. So, you are going to write x, y and 0, and here you are going to write 0 0 and minus d f. So, these two zeros are coming from here, and this is minus d f, and this 0 is coming from here. So, this you can write as minus x minus y d f I plus x d f into j. Now, r c p cross f r is equal to integral of r cross d f. The right hand side here is the moment of the distributed force, and this is the moment of the resultant force, a concentrated load at the point r c p. So, this is a vector equation. It has three components. Of course, in both cases the z component is 0. So, if you equate the I component, you are going to have minus y c p f r is integral of minus integral of y d f, and if we equate the j component, you are going to have x c p into f r is equal to integral of x into d f. So, in the first equation here you have minus sign on the left hand side, minus sign on the right hand side. So, it cancels out, and you can write y c p as 1 upon f r into integral of y d f. d f is here the scalar. So, this is 1 upon f r integral of y, and d f is p d a. So, when you want to find y c p, you have y multiplied by p integrated over the surface. Similarly, if you look at x c p, it is going to be 1 upon f r integral of x d f, which you can write as 1 upon f r integral of x, and d f is p d a. And f r we have already seen is p at the centroid times the area. So, these two are the equations which you can use to find expressions for y c p and x c p. This is y c p. All right. Now, of course, this pressure is the surface pressure at the surface. So, it is better to put the subscript s here to emphasize that this is a pressure at z equal to 0. So, this P s we have seen is minus rho g sin theta into y plus a constant of integration, which we did not find because it was not necessary. Now, we want to look at y times P s and then integrate this. So, you are going to have minus rho g sin theta in the integral of y squared d a plus c into integral of y d a. This rho g sin theta being a constant, I can pull it out of the integral. So, this is minus rho g sin theta, and this I can write as I x x, the area moment of inertia about the x axis, and this I can write as c into y c into a, where y c is the coordinate y coordinate of the centroid. Okay. Now, you can see why we have put the origin of the coordinate system at the centroid, because then y c is going to be 0. Okay. And you have a simple expression for this. So, you are going to have y c p is equal to you have to take this and substitute over here. So, it is minus rho g sin theta into I x x by f r. Now, we expect this to be negative, the reason being that you have a distributed load So, if this is your inclined surface, if you show the pressure, it is going to increase as you go down. So, you have a distributed load like this. Of course, it is not increasing linearly with y, but with z, and that is why you have the sin theta component. But as you can see that the intensity of the stress, intensity of the normal force is increasing as you go down. So, you expect that yCp will be below yc, and yc is 0. So, the expression which you have got agrees with your intuition. Now, let us find the xCp. So, we have found Ps is minus rho g sin theta into y plus c. Now, we want to multiply this by x and then integrate. So, you are going to have minus rho g sin theta, which is a constant, into integral of x y dA plus c into integral of x dA. So, this I can write as minus rho g sin theta into I x y, where I x y is the product of inertia, and this I can write as c into the x c into a, because x c is 1 upon a integral of x dA. So, this integral x dA I can write as the x coordinate of the centroid into a, and again you can see why we have put the origin at the centroid, because then you have a compact expression where this is 0. So, you are going to have xCp is equal to minus rho g sin theta I x y divided by f r. Now, this is going to be 0 if the cross section is symmetric. So, for example, if I say this is my inclined surface and the other view is a rectangle, let us say. Now, the centroid will be a geometric center, this is y and this is x. So, this is the centroid. Now, x the center of pressure will be below this c, but at x equal to 0, because now here your I x y is 0. Similarly, if you take say a circle, I will draw another figure. This is a one view and the other view suppose is a circle. Now, again the centroid is at the geometric center, this is x and is y. So, again by symmetry you will find that I x y will be 0. So, x c p will be 0. So, the center of pressure will be somewhere here below this. Now, let us look at force on curved submerged surfaces. So, we will take a familiar example. Let us say you have water and air above, and you have a surface, solid surface here, which is curved. Now, suppose I say this is x and this is y. According to this coordinate system, g y will be minus g and g x will be 0, because the gravity vector is this way. Now, if I take a small area element on the upper surface and I say the normal to this is n, and I will put this caret sign or hat sign to indicate that it is a unit vector. That means, magnitude of n is, which is root of n x square plus n y square, is 1. So, this n now is n x I plus n y j. The z component is 0. This is a plane. In this direction there is no curvature, let us say, in the z direction. Now, if you look at dF, the force exerted by the water on this, it will be along this direction and it will be pointing inward, because it is a compressive force. So, this is minus P dA into n. So, if n is pointing into the fluid from the surface, the force is going to be in the minus n direction and its magnitude is P dA. Now, if I take another area element, you have to note that because of the curvature of the surface, the orientation is different. So, here the force, elemental force, will be in the normal direction again, but the normal direction has changed. So, this n is no longer a constant, but if you want to find f, you can simply write the vector f as integral of df, which I can write as minus integral of this minus P dA n. Now, if I write n as n x I plus n y j, I can write this as minus integral of P n x dA I minus integral of P n y dA j. Okay. So, if I say f, the resultant force is say f x I plus f y j, then you have f x is equal to minus integral of P n x dA and f y is equal to minus integral of P n y dA, where the integration is carried out along the curved surface here. So, this pressure is not the pressure at any point, but at pressure on the point on the surface. If you want to emphasize that, you can put a subscript s, but the moment you write dA here, it is obvious that it is the pressure on the surface of this. Now, I will draw that figure again. So, this is the water level, this is a free surface, and quite often this is denoted by inverted triangle with 3 lines below. So, this is a symbol which indicates that above here the pressure is P atmosphere. Now, let us say this is the curved surface and I had chosen a coordinate system with x was this way and y x is horizontal, y is vertical and z is also horizontal. Now, if I take a small area element somewhere here, if it is an infinitesimal area element, this is like a plane surface which is tangent to this curved surface. Okay. So, if I draw this line here, if I say this angle is theta, let me draw an enlarged view. Suppose this is the surface and this is my area element, exaggerated. Let us say this is the horizontal line and this is the vertical line. This angle I am calling theta. Now, the unit normal to the surface is in this direction. Now, if this angle is theta, then this angle here is 90 minus theta, and hence this angle is also theta, and this has unit magnitude. So, this is the unit vector. I can write it as the sum of this vector and this vector. Now, the length of this arrow will be cos theta and this will be sin theta. So, this is cos theta and this is sin theta. So, we can write n as cos theta j minus sin theta I. So, that means we have n x is minus sin theta and n y is cos theta. Now, if I draw this triangle over here, then this is dx and this is dy and this is say dl, and my dA I can take to be dl into unit depth in the z direction. So, if you look at n x times dA, I can write it as minus sin theta into dA, which is minus dl sin theta. Now, dl sin theta is going to be equal to dy from this triangle, and dy into 1 you can say is dAx, that is the area element which is perpendicular to the x direction. Similarly, if you look at ny dA, you can write it as cos theta dA, which is dl cos theta, which is dx. So, in the tutorial session we will solve problems where you can find out these integrals for a case. This might be looking a bit abstract, but finally what you will have is, in this case f x is minus integral of p on the surface, and n x dA we showed was minus dy, and you put the appropriate limits of integration, you will get f x. Similarly, f y will be minus p integral of p s dx. Now, let us look at another application, how to measure pressure, and you know that you can use manometers to measure pressure. So, we will consider a simple case where you have a gas in a bulb and a U tube. So, you may have a gas over here whose pressure you want to measure, and you have a manometer liquid here. We will say the density of this is rho m. So, this could be water, it could be mercury, whatever it is, and this side is open to the atmosphere. So, in the lab what you can do is measure this height, we will call h m, the manometer deflection, and from this we want to find what is the pressure in the gas. So, if I say this is z and gravity is in the minus z direction, this is my datum. Let us say I call this point A, and this level I call 1, and this I call 2. Now, this is a continuous mass of liquid, and the pressure at the same horizontal level will be the same, because we have found that pressure varies only with the height. So, if I take a point here and a point here, the pressure will be the same. So, if you want, you can call this 3. Now, we know that dP dz is minus rho g, this we have seen. So, if I look at this, if I integrate this, you are going to have P 2 minus P 3 is equal to minus rho g Z 2 minus Z 3. If I integrate this from 2 to 3, you will get this expression. Now, P 3 is equal to P 1. And if you want the difference between P and P at this point A and 1, again you have to use a similar expression with a different value of density. So, this is the density of the manometer fluid, rho m, and here you are going to have, say, if you want, say, P A minus P 1, you are going to have minus rho of the gas, which you are taking to be a constant, into Z A minus Z 1. Now, this density of the gas is usually small, so you can neglect it and say this is approximately 0. So, if you know what is P 1, you know what is the pressure in the bulb, pressure of the gas in the bulb. So, P A then you can say is approximately P 1, P 1 is the same as P 3, and P 3 from here is P 2 plus rho m g Z 2 minus Z 3. Now, Z 2 minus Z 3 is H m and P 2 is P atmosphere. So, P A then we can say is equal to P atmosphere plus rho m g H m. So, rho m is known, g is known. So, if you measure H m, you can find what is the pressure. Now, you can define a term which is called gauge pressure. We will call it P gauge, which is defined as P minus P atmosphere. Now, P cannot be negative, but P gauge can be negative. If P gauge is negative, it means that the pressure is below atmosphere. If P gauge is positive, it means the pressure is above atmosphere, and if the pressure is atmospheric pressure, then the P gauge is 0. So, if you want say here P A gauge, by definition that is P A minus P atmosphere, which is simply rho m G H m. So, by measuring H m you can find what is the gauge pressure. So, we have looked at what is called a U tube manometer. Now, let us look at what is called an inclined manometer. So, here what you have is an inclined tube. And you have a container here which has the now let us say this is the container which has the manometer fluid, which is a liquid. Now, let us say I denote by a horizontal line the level when the pressure at on this side is atmospheric pressure and the pressure here is atmospheric pressure. So, here P is P atmosphere. Now, let us say here I connect this to a bulb over here and the pressure is more than P atmosphere, then what will happen is this level will go down. Now, what we would like to do is keep this open to the atmosphere and this can be connected to that bulb, whatever it is. So, if you have a high pressure here, what it will do is it will push the liquid down here and move it, push it up over here. So, let us say when you have a pressure here, this has gone down and this liquid has gone up, let us say this much. Now, what we will do is we will have a scale which is inclined and we will read this distance, we can call it say L. Now, we want to know, so this side is P equal to P atmosphere and here you have a pressure here at the free surface, which is the same as this is a gas and this is your liquid, the manometer liquid, this is also liquid and here you have air, let us say. We want to know what is the gas pressure. So, in other words, we want to know what is the pressure at this level. Now, this is one continuous mass of liquid. So, if I draw this horizontal line here, if I call this say 0.1 and if I call this 0.2, then we know that P 2 is the same as P 1, which is what we want to measure. And if I call this 0.3, then the pressure is going to be higher than the pressure at 3. So, we are going to have, let us say this is I can have any datum here, maybe here, and this is my Z and gravity is downwards. So, P 1 we can say is equal to P 2 and P 2 will be P 3 plus rho of the manometer liquid, which we are calling rho m G into this vertical distance between this level 2 and this level 3. So, if I say this angle is say theta, angle of inclination, this is L. So, this angle is theta, this is going to be L sin theta. And this P 3 is going to be your P atmosphere. So, this is P atmosphere plus rho m G L sin theta. Okay. Now, actually I missed something here. Suppose I call this distance delta, this is L sin theta plus delta, because L sin theta is only this much. So, let me draw that figure again. So, first of all I will draw the initial level of the manometer liquid, which is in dotted lines. What it means is that if you have a connect this to a gas chamber where the pressure is atmosphere, then the liquid level will be here in this container and here. Now, suppose the pressure is higher, so this will be pushed down, and the liquid is pushed up over here. So, this is the liquid level here and this is the liquid level here. Now, your scale will measure this distance, inclined distance in this along this inclined line from the initial level up to the level to which it rises. Okay. So, this distance here is L sin theta, if this angle is theta, and this much we are saying is delta. Now, we wanted the pressure of the gas, which is the same as the pressure at this point. Pressure at this point is the same as the pressure at this point, and the pressure at this point is the same as atmospheric pressure plus rho g times this height. So, we are saying that P 1 is P 2, which is P atmosphere plus rho m g L sin theta plus rho m g delta. So, we need to find what is delta. Now, let us say the small a is the area of the inclined tube and capital A is the area of this container. Now, the volume of liquid which goes down over here will be equal to the volume of liquid which is going up over here. So, from conservation of volume of this liquid, you are going to have A into delta. See, this height delta means this is also delta. A times delta is the volume of liquid which has been pushed down from this dotted line. So, this will be equal to the small a into L, which means that delta is A upon A into L, which we can substitute over here. So, ultimately we will have P 1 is equal to P atmosphere plus rho m g L sin theta plus A by A into L. So, if you know what is small a and what is capital A, you can have this correction, but usually this is going to be small. Usually you are going to have A by A much less than 1. So, if you want to know what is L, from here you have L sin theta will be approximately P 1 minus P atmosphere by rho m g . So, what we have done is we are trying to estimate what is L. So, this term here is being neglected. Now, in any measurement you have some error. The measurement cannot be more accurate than the least count of your scale. So, if I say the least count delta L is the uncertainty in the measurement. So, this may be of the order of say 1 millimeter typically. Then you have a relative error in the measurement, relative error in measurement of L, which you can estimate as delta L by L. So, you can see that if you want the relative error to be small, then your L has to be large. Okay. Now, L sin theta is the difference of the applied gas pressure with this P atmosphere divided by this constant, and you have the sin theta factor. So, if sin theta is small, then L will be large. For example, if I say theta is 30, sin theta is half, and L will be double of this difference. On the other hand, if I said theta is 90, then L will be simply this. So, there is a factor of 2 involved here. So, the advantage of this inclined manometer is that this L is for a given pressure difference which you want to measure, the length L or the manometer reading is going to be large, which will reduce the relative error in the measurement. So, the measurement of the pressure is going to be more accurate, and that is why this is commonly used in the lab, and it is a very simple apparatus. Now, of course, when you make the when you do the calculations, you need not neglect this A by A times L term. This I have neglected just to explain how the sin theta is affecting your making the measurement more accurate.
টাইম আছে হবে পরে
I think we will continue after lunch. We will look at other topics. Since there is only 5 minutes, I think we can answer some questions. Questions.
এখনই
We could use that time, or we can take a break.
স্যার কোশ্চেনস আমরা দেখে রাখবো, এখন দেখে রাখছি, তাহলে পরে এসে আমরা পরে এসে আপনি আনসার করে দেবেন, আমরা এখন দেখে রাখছি কি কোশ্চেন।
আচ্ছা,
আমার সেটাই ভালো হবে, বলে দিন স্যার আপনি 1 আওয়ার ব্রেক।
Okay, so we will break for about 1 hour, and we will come back at 2 o'clock.